Thank you. Thank you very much. Thank you for the kind introduction, Marcus. So allow me to inform you a little bit about the latest developments for titanium dioxide-based smart and functional coatings. First, so nanomaterials, by definition, are materials smaller than 100 nanometers. And nanotechnology is defined as the systematic modification of materials in a range of 1 to 100 nanometers. So really on the molecular to say sub-virus level. So you see here a bit where we are in this range, really on the left side of this scheme. Oh yeah, I want to tell you this afternoon, I should not make promotion, but this afternoon is session 12 in the Kiev room about nanotechnology, which I will be hosting, and I really invite you to go there if you have interest to learn more about nanotechnology. So nanomaterials are based on base chemical materials, basically. You make them into precursors. These precursors form into particles or in two-dimensional sheets or in supramolecular structures. And then you process them and you come into end application as smart textiles, as smart drugs, as electronic sensors, or smart coatings that you can deposit on any material you like. So most nanomaterials can be made from some kind of a chemical synthesis and do not need to go any mechanical processing. Nanotechnology is often referred to as the bottom-up method, in contrary to the top-down method, where you need to crush and to mill particles to small particles. A process normally costs a lot of energy because you need to break down a thermodynamically favorable position. I can do this, yeah. So smart coatings mean responsive to changes in environments, to changes to an external force. And in the case of nanotechnology, in a nutshell, this external force is light. And put very simple, when you beam light on this layer, radicals are formed from water and oxygen, which is present. Radicals then break down organic matter, which then basically breaks down into carbon dioxide and water. And with that, these kind of materials can become self-cleaning, air purifying, or antimicrobial. So in this presentation, we're going to take a closer look on the mechanisms behind this. So first a word about sol gel. So a wet chemical process to come to nanoparticles is the sol gel process. And what it is in a nutshell is that you basically start with metal alkoxides. Metal alkoxides are hydrolyzed into metal hydroxides. These hydroxides can condensate into metal oxide metal bonds with the release of a small amount of water. Now the metal you can choose can be from zirconium to titanium or silicon. I think the most abundant use is indeed silicon. And if you have a metal alkoxide with a valency of 4, which means that all sides can react, you create a very dense, high cross-linked network, which typically is very hard. So mixing of metal alkoxides is possible, for example, with a type with a very specific chemical function. So in the case of nanotitanium dioxide, so if you run this process, for example, with titanium isoproxide or titanium isobutoxide, you can come to a nanoparticle of titanium dioxide, which typically is then anastase type, so the structure is anastat, 99%. Typically very small particle sizes of 15 nanometers, and normally you will disperse them in water, but you can also disperse them in other solvents. This process allows for doping agents. Very important, in the doping agent you can tweak certain properties of the crystal. So this modification or doping that they call is in sol gel. This is pretty widespread. Dopants are added at small amounts, with very low concentrations. Think about metal dopants as silver, platinum, or iron, but also non-metal exists based on nitrogen, boron, phosphorus, or sulfur. So the dopant you choose basically in relation to the property you want to improve. So with titanium dioxide, this might be self-cleaning, or antimicrobial, or anti-pollution. You also look at the ease of use, how easy is it to mix in, and of course, at the economics of it. So, nanotitanium dioxide can break down organics, that we saw in the beginning. But how does it actually work, and what role does this doping agent then play? Well, titanium dioxide is a semiconductor, which means that electrons can be excited and fall back. And when they fall back, they generate radicals from water and oxygen, which is already present on the surface. If then organic matter flows by, basically they get in touch with these radicals, and you get a radical reaction, and basically your organic matter breaks down into smaller parts, that breaks down in even smaller parts, and in the end you end up with carbon dioxide and water. So this process is catalytic, perpetual, runs under the influence of light, in fact UV light. So what you need to do, you shoot basically this electron from one band, the valence band, to the conduction band, and for that you need light with the energy of about 400 nanometers, which means UV. So what you can do with such a doping agent is that you reduce this band gap a little bit, and with that you make this thing visual light active. So you need light of less energy, and then this nanotitanium dioxide becomes visual light active, and for example you can use it interior. So how do you get to a coating, from precursor to coating? Well, it's basically a three-step process. You synthesize the sol, you apply it, and you cure it. So your precursors go into a sol. This is applied. You go from a gel to a film gel. And in the end, you get your cross-linking, and you get a very hard coating. So it's very typical for the sol gel processor that you make ready-to-use coatings from the precursor. In that sense, it's a very efficient process to coat something. So let's look at how this is applied. So the application conditions we have shown here. So we use a simple spray coater, a Krautsberger conventional spray coater with a nozzle size of 1 millimeter, pretty small, at a pressure of 3 bars. And at a distance of 20 centimeters, you go left and right over the panel. And if you want to have 2 passes or 2 layers, you go again from up to down, and you can go up to 3, 4, 5 passes. So what you see already here is that if you take multiple passes, you will increase your opacity, which you actually can measure by a haze measurement. So you basically measure the transmission. So of neat glass has a transmission of 100% and a haze of 0. And if you apply, say, 1 pass or 2 passes of this material, you will see that you go to 1% of haze. And if you go up 2, 3, 5 passes, you go to 4% of haze. So what is very important here, if transmission is your goal, you shall apply very thin layers. And this is, for example, the case with solar panels or with car windshields that actually have this specification of 1%. Also important to say that this does not play a role if you want to coat something matte or concrete or something. And of course, this does not play a role. You can apply as many layers as you like. So when we had this layer, we made a SEM picture, so scanning electron microscopy. And what you preferably like is a very open structure, because the more open the structure, the longer the travel time of an organic species, and the longer you have time to break it down into its compounds, carbon dioxide and water. So open structures mean longer travel time. Well, what you can see on this picture that the structure is indeed very open, as you have valleys and hills. And you can also deduct that the particle size is about 16 nanometers, so very small. We also checked the surface roughness by atomic force microscopy. So in this case, you go over the surface with the tip, and the tip follows the surface, and you can measure 2 main things here: the amplitude of the tip, so how big are your valleys and your peaks, which was 200 nanometers, and we found an average roughness of 29 nanometers, which is twice the size of a particle. Well, does it then work? So we performed some practical tests to check the breakdown of organic matter, which is promised by this mechanism. And I'd like to go over this slide, but bear with me on this slide because it's a complicated one. So the test we followed here is the ISO 27448, which is simply a test that prescribes that you break down an organic matter. The model compound here is oleoic acid, and you really measure the performance of the coating to break down oleoic acid. So what you do, you apply your coating on your plate, and then you dip this into your oleoic acid solution. You do the same with the blank, so you also dip it in an oleoic acid solution, and then the value you're gonna follow is the contact angle, and the contact angle of water to this surface. But just to say something about the contact angle of water on a normal surface, say, is about 70, and if you go very low, super hydrophilic, you go to a contact angle of water with this surface of below 10. It means that it is very hydrophilic. So what did we measure here? If you look at the sol gel coating, the contact angle of this thing was lower than 5, so very low, super hydrophilic. We also measured the contact angle of the part which was drenched into this oleoic acid. There it is 90, so much higher, which is logic because oleoic acid is oleophilic, so hydrophobic. And on the blank we did the same, so we measured the contact angle of a water droplet on oleoic acid. In this case it was 80. So the difference between these two of 10 degrees probably has to do with the fact that we create some kind of surface morphology there, which means that normally the contact angle increases. So and then you run the actual test, which is you beam the plate with UV light. So UV light of 1 milliwatt per square centimeter, which means this is, say, outdoor light, comparable with outdoor light. So you measure the contact angle of the plate when it is beamed, and you see that this contact angle goes down very rapidly. So after, say, about 8 hours, you're already below this 10 mark, which means that the oleoic acid is gone, it has disappeared. So it is basically broken down into water and carbon dioxide. This can only be explained like this. And you also see that the blank does not change a lot. So it went from 80 to 78 or something. So it keeps this very high contact angle, and if you take it out of the test, you still see that there is oleoic acid on this. So this test basically proves the self-cleaning ability of these materials for organic matter. So a word about superhydrophilicity. We showed you the superhydrophilicity is defined as a contact angle smaller than 10. So where does it come from with titanium dioxide? Well, but basically titanium oxide bonds under the influence of light and water tend to split, so you get titanium hydroxide. So in this picture, you go from left to right. This is not hydrophilic at all, and if you go to the right side, you go to something which is super hydrophilic. So it's in equilibrium, but if there is light and water available, you go to the right side of it, so you make something super hydrophilic. So this superhydrophilicity is related to something, is related to the antistatic property. And in fact, the antistatic property is basically related to the electrical property of a surface. And it's expressed in surface resistance. So you can analyze this with a 4-point probe. So you have your glass plate, and on 4 sides, a glass plate with coating, and on 4 sides you measure the resistance of the coating. And in this case, we measured the resistance of 2.3 10 to the 8 ohm per square. How it is expressed, which means that such a material is statically dissipative. It also means it's antistatic, and also should mean that it is dust repellent. And shall repel particles. But this is what we tested in a practical test. So we looked at the antistatic property and superhydrophilicity. So what you see here is a plate. The left side is coated with this nanotitanium dioxide coating, and the right side is not coated. And you see if you throw carbon black to this, then on the left side it doesn't stick so much, but on the right side it does much more. And this, we believe, is related to the fact that it is antistatic and dust repellent. Well, moreover, We then applied some water on this. So we did, say, a rain simulation test. And we sprayed with a spray of water. And you see that on the left side, with the coated piece, water tends to sheet down, which is a typically from super hydrophilic surfaces. So water sheets down and it takes along the carbon black. And you see on the right side, this is not happening. So this is relatively hydrophobic. Droplets stick, and this plate, which is not coated, tends to be dirty. So here we measured the anti-static properties. And in this test, you really see a nice comparison of a nice combination of this anti-static property together with the super hydrophilicity. So yet another test to follow for dirt pickup is this EN1096, a test developed by the glass industry. So here the dirt is a combination of organic and inorganic matter. So the organic part is stearic acid and adipitic acid. Combined with inorganic parts based on clay, calcium, and all kinds of salts. So in this test, you spray the dirt on the glass plate. You let it dry for 1 hour at 60 degrees. You radiate it with UV. You water spray it, dry it, and then you analyze the haze. And we saw this before. So this haze measurement, you can already see the two plates. So this is the plate coated, the plate non-coated. You see a clear difference in dirtiness. And for the salt gel coated, the haze was, say, around 1%. We know that the coating gives this effect. And with the non-coated one, you saw that this goes much higher to 4%. So as a measure of how dirty the panel is. So our practical use is on solar panels, so to make self-cleaning solar panels. So we went to a solar park and we tested this coating, and we used 2 strings. So one string of solar panels was coated, string 1, and we compared it to a string 2, which was non-coated, and we compared the relative performance of them. And what it means, relative performance, if the performance is 100%, they would perform the same. What you see is that initially, say in the first 2 months that we did this, you see a haze effect of the coating, so you perform a little bit less. So string 1 performs a bit less than string 2. But after 2.5, 3 months, you see this self-cleaning effect kicking in, and these panels start to produce more energy. So 1 to 2% does not seem a lot, but if you think about a gigawatt solar farm, this is really millions of euros per year. So very nice practical effect of this self-cleaning. Other nice example, street in Vienna, building cleaned, coated 5 years ago versus the same non-coated. You see clearly a difference in cleanliness. Titanium dioxide as indoor air pollutant. Formaldehyde is used as a model compound for air pollution. So formaldehyde is typically present at ppb level, so up to 100 parts per billion. But it can increase up to toxic ppm levels if you introduce new furniture or laminate in your room. So there is a norm to follow how good this can be broken down. This norm is 22197, where you basically measure the reduction of formaldehyde in a closed room by GC. So there's a closed room, you have your plate of coating, and you basically measure in this room the formaldehyde reduction in time. So you see when it was coated, or the coated plate was put in, you have a 55% reduction of formaldehyde. And if you compare that to the one with only light, it's 5%, and if you have no light or no catalyst, it's even not broken down. And this technology is today used. It's used in air purifiers equipment that are sold on the internet or in specialistic shops for household use as well. Microbes. So by the same mechanism of radical formation, also microbes can be broken down. Radicals break down organics, including bacteria, including viruses, including fungus. And actually it's a very efficient method. So this radical formation really attacks on microbes and disrupts it completely. So there are several tests you can run. One of the tests is ISO 22196, which is a test on plastic. So what you do here, you have You have a piece which you coat. This you coat, or this you challenge then with bacteria, and you look basically in a situation where no light is used, by the way, what happens to the bacterial count. And you see that it reduces in 24 hours in the case of this Listeria monocytogenes. You see that it reduces with a log 5, and you see that the comparative, which is uncoated, does not reduce a lot. And this is the same effect you see with E. coli, with Staphylococcus and Pseudomonas. Just to remind, log 5 means 100,000-fold reduction, or 99.999% reduction. Compared with your household disinfectants, often does not go further than 99.9%, so this is 100-fold more. Also works for viruses. In this case, coronavirus we tested, so in 24 hours also we saw a log reduction of 5. Practical use here, a medical room. So here we had 2 medical rooms. We measured the bacterial count. In the beginning there were 50 to 60,000, say. We disinfected the rooms. With room 2 we coated it, so the ceilings and the walls, with this nanotitanium dioxide, and we followed the bacterial count in time. And you see that it really does not increase in 6 months, whereas the control room, which was not coated, you see the bacterial count rapidly going up. And this was, by the way, analyzed by the ATP luminescence method. So in conclusion, I showed you the Soldial method to produce ultra-small particles of nanotitanium dioxide. We saw that these particles, or the coating basically, has a very open structure and therefore increased contact with any material, any organic material. It was proven self-cleaning, and so it gave the ability to break down organic matter. We saw that it was anti-static and dust repellent. We saw this very nice super hydrophilic water sheeting effect with the dirt coming down. And we saw a number of practical tests, notably the solar panel test, where we generated more energy from these solar panels. And by means of the exact same mechanism, these materials can also be air purifying and also antimicrobial. And with that, I'd like to thank you for your attention.